This is lesson 5.1, length and dot product. Two important pieces of information to know and be able to work with when we think about vectors. There's a lot of applications that you can do with vectors, and we kind of saw that in chapter 4 when we thought about a vector being part of a matrix, where we talked about the row vectors and column vectors that make up a matrix. And in that regard, we can think of a vector as something that can hold a lot of data. And we can then, if we have vectors that are each holding data where the elements are the same, or at least from one vector to another, element 1 might be a certain piece of information, element 2 might be a certain piece of information. And we can start to combine and manipulate those vectors to work with data. The other thing is more in the realm of physics, where we might think about vectors as force. And how two vectors or two forces are acting on an object, and what the ultimate result is of those forces acting on that object. Especially in the latter type of applications, we really need to be thinking about length and dot product. They're two important parts when we get into those types of applications. So we're going to start by looking at length. And length is simply the magnitude of the vector, or maybe better said, magnitude is the length of the vector. And rather than just dive into this definition here, let us construct this kind of geometrically. We talked before about vectors having a horizontal and vertical component. So if I draw on a vector, I can think of that vector as having two components to it. It has this horizontal component, and it has this vertical component. And if we think about adding two vectors together, if I add the horizontal and I add the vertical tail to tip, right, here's the tail to tip, that resultant is this vector that I initially drew. Okay, so I'm going to call this terminal point v1, v2. We're going to call this vector v. And I'm going to call the other ones just v1 and v2, so that basically this vector and this vector, if we think about the length of that vector, if we think about the magnitude of v1 and the magnitude of v2, their lengths, that's going to give us this ordered pair v1, v2. Okay, so just trying to make some of those connections. So if I want to think then about this idea of length, really what ends up happening is, if I know v1 and v2, if I know those horizontal and vertical components, and because they're horizontal and vertical, they make this 90-degree angle, we have a right triangle. And in essence, then we can use Pythagorean theorem in order to find the length or magnitude of v. So very simply, the magnitude of v would be equal to basically the magnitude of v1. And I should say v squared, right? It's a squared equals b squared, or a squared plus b squared equals c squared. So these are all squared. So that's going to be squared plus the magnitude of v2 squared. And if I take the square root of both sides, then the magnitude of v, or vector v, is simply the square root of, and I'm going to drop those magnitudes and just think of it more in terms of this ordered pair, the terminal point, because that is really, v1 is the magnitude of that vector, v2 is the magnitude of that vector. And so just to simplify this, let's just write it like this. So in other words, and this again extends to any n space. If we were in 3 dimensions, this would work exactly the same way. 4 dimensions doesn't matter. The point is, no matter what dimension you're in, if you just square each of the components within that vector, add them together, take the square root, that is going to give you the length or the magnitude of that vector. Okay, so I think fairly hopefully straightforward concept here. And so let's go ahead and take a look at an example, just a real simple example here. So we're going to be in the 4 space. Obviously, we can't really represent this visually, but if whatever this is, we want to find the length of it. So to find the magnitude of v, we simply take the square root of each of those components squared. Add them together, square them up. So we've got 2 squared is 4, plus 1 is 5, plus 9 is 14, plus another 25 is 39. So very simply then, the length or magnitude of v is 39. That's how we find length. Again, it doesn't matter what space you're in. You just do that for all the components. All right, well, if that's the case, then we could basically then also extend this to scalars as well. And this idea that if I have a vector v and c is a scalar, then whether I multiply the vector first by the scalar and then find its length, or find the length and then multiply by the scalar, it doesn't matter. Order does not matter here. So that in and of itself isn't all that like maybe earth-shattering or important, but it does lead into the second theorem that we've got here. And this simply says that if v is a non-zero vector, then the vector magnitude u is equal to v divided by the magnitude of v. All this is saying is that if I have a vector, this is how we turn it into a unit vector. Okay, so if I have a vector v, I can simply divide vector v by its magnitude, by the magnitude of v, and that's going to give me a unit vector u. Okay, so here's how this looks. We've got a unit, we want to find the unit vector in the direction of v, given 3, -1, 2, and verify that this vector has length 1. So very simply, what we're going to do is we're going to find the magnitude of v. Just like we did before, we're going to take 3 squared plus -1 squared plus 2 squared, which is 9, 10, square root of 14. Now I'm going to leave it square root of 14. I'm not going to put it into a decimal because I don't want to lose the accuracy of that number. What that means then is that the unit vector, if we call this unit vector u, that vector has the components 3 divided by the square root of 14, -1 divided by the square root of 14, and 2 divided by the square root of 14. That would be the unit vector in the same direction as v. Okay, we've basically taken v and basically compressed it down into a length of 1. So then to verify that this has a length of 1, let's go ahead and find the magnitude of u. And if we did this correctly, we should get a value of 1. So we've got 3 over the square root of 14 squared plus -1 over the square root of 14 squared and plus 2 over the square root of 14 squared. All right, so in this case, in the numerator, obviously as we square these, the denominator is just going to be all over 14. In the numerator, we'd have a 9 plus 1 is 10 plus 2 is 14. In the denominator, the square roots go away. We just have over 14, and sure enough, square root of 1 is 1. So that just shows that indeed this u that we found is the unit vector of v. All right, or in the direction of v. All right, well, let's talk then about distance between vectors. So we've talked about the length of a vector. What if I wanted to find the distance between two vectors? So suppose, for example, and again, I'm going to kind of draw the picture first, and then we'll kind of go back to the definition and look at that. Let's just say I've got two vectors. We'll put one here, we'll put one here, and we'll call this u and v. And so let's give again terminal points here, u1, u2, and v1, v2. v1, v2. And so again, let's suppose that, for example, I wanted to just find the distance between these. I'm not talking about a vector, I'm just literally the distance. Well, if you think about what we have here in terms of what we've talked about before, we have two vectors, the blue vectors u and v are right now, they're tail to tail. So when I draw that lengthen, that purple lengthen from one vector to the other, what I'm really doing is I'm finding that could represent a vector that is the difference of u and v. If you recall, if I wanted to find u minus v, right, u plus v, like we did before, we put them tail to tip, right? We put them tail to tip, and then that gives us the resulting vector when we add those together. So v here is really v1 plus v2. Those vectors added together are going to give us the vector v. But when we put those vectors tail to tail like this, the vector from tip to tip or head to head is going to be the difference of those vectors. So I'm going to call this d, the distance from u to v. And that distance from u to v is really then the magnitude of u minus v. Just the difference of those vectors, we're going to find the magnitude, which is the length or the distance between them. So in this case, that's going to be represented by basically taking u1 minus v1 and u2 minus v2, which is the square root of u1 minus v1 squared plus u2, oops, that should be a 1. Let me erase that and write that correctly. That should be a 1. And then u2 minus v2 squared. Notice that all that is the distance formula. That's all it is, right? The distance formula in two dimensions, at least in the two-dimensional space, is x minus x1 or x2 minus x1 squared plus y2 minus y1 squared. We take the square root of that. That's the distance between 2 points in the xy coordinate system. So a lot of what we're doing here is nothing new. It's nothing special. We're just really taking a lot of math that you probably learned, even back in high school, geometry, algebra, things like that. And we're just kind of putting this new skin of vectors over a lot of those mathematical concepts that you learned. So with that, let's go ahead and just do an example here. So we're going to find the distance between these two vectors in the 3 space. And so again, to find the distance between those, let's go ahead and I'm just going to do this. Let's just take the magnitude of the difference 1 minus 2. I'll actually write this out just so if you really need the example here in full detail, we've got that. So this is what we're doing, right? We're finding the difference between those vectors. In this case, I just took u minus v. And now we're going to, just like we would find the magnitude of any vector, we're going to just take those differences, square them, and take the square root. So in this case, 1 minus 2 is a negative 1. We're going to square that. Plus negative 2 minus 0 is a negative 2. Square that. And 4 minus 5 is a negative 1, and square that. And so we've got 1 plus 4 plus 1 is 6. And so the square root of 6 is the distance between those two vectors. All right, so that's kind of everything regarding length and distance. Let's now kind of flip and let's talk now about this idea of dot product. So this is kind of the other big topic in this lesson. So it tells us that the dot product of u and v being two vectors, is the scalar quantity where, notice this is the symbol for u dot, or for the dot product. So that little dot in the middle, that just means it's the dot product of u and v. And the way that we find that is we take u1 times v1 plus u2 times v2, and you keep going for as many components as you have in the vector. So very simply, if I want to find the dot product of u and v here, I'm going to take negative 3 times 1 plus 4 times negative 2, and that's negative 3 minus 8 is negative 11. That's the dot product. So with that, we're going to talk about one theorem, and then again, this is not in and of itself, it's not important, but when we get to the next idea, I'm going to come back to this, and we're going to see why this Cauchy-Schwarz inequality actually makes sense and the necessity of it. So this one just says that if u and v are vectors, then the dot product, the magnitude of the dot product, is less than or equal to the product of the individual magnitudes. All right, so in other words, if I find the dot product of u and v, okay, this is just a scalar, right? So this is basically saying if I take the absolute value of that negative 11, so if I make this 11, that if I was to now find the magnitude of u and the magnitude of v and multiply those magnitudes together, that is going to be greater than or equal to 11, okay? Now, like I said, that may not make a whole lot of sense right now, and why? So what's the importance of that? Well, let's move on, and we'll do an example, and then move on, and we're going to see why this is important or how this gets used. So verify the Cauchy-Schwarz inequality for u equals 3, 4, and v equals 1, 3. So very simply, again, if I find the dot product first, we'll do that side first. So dot product of UV is, again, just 3 times 1 plus 4 times 3, which in this case is 3 plus 12 is 15. Okay, now we're going to find the magnitude of U. So magnitude square root of 3 squared plus 4 squared, which is square root of 25, or just 5. And then we're going to find the magnitude of V, which is the square root of 1 squared plus 3 squared, which is the square root of 10. Now, you could, if you wanted to, convert 10 into a decimal, but we know that the square root of 10 is bigger than 3. Obviously, square root of 9 is 3, so square root of 10 is bigger than 3. If I multiply now the magnitude of U times the magnitude of V, we get 5 root 10, which we know is bigger than 15. Okay, that's going to be greater than 15, which again demonstrates the Cauchy-Schwarz inequality. Okay, now let's talk about where and why this is a little bit important. So let's now talk about angle between two vectors. And I'm going to go into a pretty in-depth problem here, or process, in terms of showing why this works. It says the angle theta between two non-zero vectors in R can be found using cosine theta equals the dot product of UV divided by the product of their magnitudes. Okay, and in this case, theta is between 0 and pi. Okay, so this is basically saying if I have two vectors and I want to find the angle between those vectors, and I didn't mean to make that look quite 90 degrees, but if I wanted to find that angle between the two vectors, we're going to call this vector U, and we're going to call this vector V. And so I'm going to give these terminal points V1, V2, and U1, U2. Okay. So if you kind of look at this setup right now, if I were to connect the tips of these two vectors and create a triangle, I have, if I look at the magnitude of U and the magnitude of V, those lengths, I basically have a setup where if I wanted to find this side, the magnitude of U minus V, I could do that using law of cosines. So just to remind you, if you've forgotten law of cosines, maybe it's been a while, law of cosines basically says that in a triangle, that a squared plus b, or excuse me, a squared equals, sorry to write the Pythagorean theorem there, a squared equals b squared plus c squared minus 2bc times the cosine of theta. In other words, a, b, and c are just the three sides of the triangle, and a is always the side opposite the angle. So in this case, if we're looking for angle theta, then this side opposite it, which is the magnitude of U minus V, would represent A in this equation. Okay, so let me make the substitutions now with these magnitudes. So given that, then the left side becomes the magnitude of U minus V squared is equal to, and now it doesn't matter what we call B and C, I'll just use U for B and V for C, so magnitude of U squared plus the magnitude of V squared minus 2 times the magnitude of U times the magnitude of V times the cosine of theta. Okay, this is where it gets kind of fun. We're going to actually multiply all of this out and see what happens. So on the left side, the magnitude of U minus V, again, means we have to take U1 minus V1, square it, and then plus the magnitude of V2 minus, or U2 minus V2, and square that. So on the left side, we would have U1 minus V1 squared plus U2 minus V2 squared. Now notice I don't need a square root over this because we're squaring these, right? We're squaring this magnitude, and so the magnitude itself would require a square root, but because we're squaring that magnitude, we basically get rid of the square root. So that's going to be our left side. On our right side, the magnitude of U squared is going to be U1 squared plus U2 squared. And then plus the magnitude of v is v1 squared plus v2 squared. And then minus 2 times those same quantity. Or actually, I think in this case, and you'll see why, I'm going to leave this. We're going to leave this magnitude u and magnitude v. All right, on the left side, let's go ahead and expand those out. So I'm going to have, if I expand those out, I'd have a u1 squared minus 2u1 v1 plus v1 squared. So that's the first set of parentheses squared. And then plus, now squaring the second set, we'd have a u2 squared minus 2u2 v2 plus v2 squared. And then equals u1 squared. I'm going to just drop the parentheses, u2 squared plus v1 squared plus v2 squared minus 2 magnitude u magnitude v cosine of theta. All right. So looking at what we have, I have a u1 squared on the left. I have a u1 squared on the right. Those cancel. I have a v1 squared and a v1 squared on the left and right. Those cancel. A u2 squared and a u2 squared and a v2 squared and a v2 squared. So at this point, what I have left is negative 2 u1 v1 minus 2 u2 v2 equals negative 2 magnitude u magnitude v cosine of theta. If I divide everything by a negative 2, u1 v1 minus u2 v2 equals magnitude u magnitude v cosine of theta. And then dividing by the product of the magnitudes, and I'm just going to turn this around, the cosine of theta is u1 v1 minus u2 v2 divided by magnitude of u magnitude of v. In the numerator, u1 v1 minus u2 v2, or excuse me, I'm sorry, that should be plus. Whoops, not that one. I divided by a negative. That should be a plus. That should be a plus. That is the dot product of uv, which is the formula that we have up at the top. That's this formula right here. So how does this connect to the Cauchy-Schwarz inequality? So remember, the Cauchy-Schwarz inequality, right, says that dot product of uv has to be less than or equal to the product of the magnitudes, okay? Which means that in this equation now that we have, right, we've got cosine theta equals this. Basically, it's saying that this has to be smaller than the denominator, okay? Why is that important? Well, in order to find theta, you have to take the inverse cosine. If I wanted to find theta, I have to take the inverse cosine of the dot product of uv divided by magnitude u magnitude v. Well, if you remember, think unit circle here. On a unit circle, right, where my radius is 1, the cosine is represented by the x value, okay? Which means that x value is never bigger than 1, and it can't be bigger than 1. If you try to take the inverse cosine of a value bigger than 1, use your calculator, try to find the inverse cosine, it's going to give you an error. It can't be done. It's impossible. So without this theorem, if this doesn't hold, then this formula doesn't hold either. It has to be true every time for this to be true. All right, so let's go ahead and let's just do an example. That was a lot. Let's just do an example and find the angle between two vectors u and v. So very simply, I need the dot product and I need the magnitude of each vector. So let's start by finding the dot product. And I guess you could, if you want to, we could do this all in one fell swoop. I think we're just going to do it that way. Let's just do this in its fraction. So the dot product, again, is just multiplying the components, 3 times 1, plus 0 times 1, plus negative 1 times 4. And then in the bottom, we need the magnitude. Now, in this case, I'm going to just do this kind of in my head, because remember, it's 3 squared plus 0 squared plus negative 1 squared. So 3 squared is 9, plus 0 plus 1 is the square root of 10. And then we're going to multiply that by the square root of 1 plus 1 plus 16 is the square root of 18. So this is going to be, in the numerator, 3 plus 0 minus 4 is negative 1. In the denominator, square root of 180. So at this point then, to find theta, we're taking the inverse cosine of negative 1 over the square root of 180. And at this point, we're just going to put this into our calculators and find the answer. And if we were to do that, in radians, this is 1.645 radians, which, just to give you context, is about 94.3 degrees. Okay, so that would be the angle between those two vectors. All right, let's wrap up with kind of one last idea here. And we're not even really going to do much with this, but this is actually an important idea. So don't let this be kind of a footnote at the end of a long lesson that you just forget about and ignore. We are going to use this concept a lot in the upcoming lessons. And basically what we're talking about here are orthogonal vectors. Okay, it says two vectors u and v in Rn are orthogonal when the dot product is 0. Okay. This word orthogonal, if you don't know already, is nothing more than perpendicular. In mathematics, when we think orthogonal, just think perpendicular. So in other words, what this is saying is if I have two vectors whose dot product is 0, they are perpendicular. They form a 90-degree angle. Okay. So I'm not going to do anything with that. Like I said, we're going to use that a lot in the upcoming lessons, so we'll see it used in those. But certainly know how to find the length, know how to find the dot product, know how to find the angle between two vectors, know how to find the distance between two vectors. And with that, we'll end this lesson, and I'll see you in the next.